All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. Everyone have a good weekend? Good, it's good. On Saturday, I actually had a kind of a fun day with my wife. She's doing some work in LA, so we stopped by the Biltmore Hotel. So if you don't know what that hotel is, it's a kind of a historical hotel in Los Angeles. They used to hold the Academy Awards there. And on the way there, my wife was kind of making fun of people who go there and recreate one of Taylor Swift's music videos, Delicate. And so while she was kind of making fun of these people, I was like, because I knew that when we would get there, she would want to do the exact same thing, and she definitely did. She made me do it too. So I'm hoping that none of you ever find my wife's Instagram because there's me doing yeah, poses to Taylor Swift's music video on her Instagram. Okay, so the plan for today, so we're done, we're done with kind of all the, I would say kind of the more background information. So today we're kind of starting with, kind of the real biomechanics stuff. So we're actually gonna be doing calculations today. So that's exciting. So we're starting with the upper extremity. It's nice, yeah. My wife loves that song too. So the way the next 3 weeks are going to be structured is that we're going to be focusing on kind of the three, I would say, kind of major sections of the body. And I'll kind of organize it because these three sections all kind of have their unique characteristics compared to one another. So this week we're doing upper extremity. Next week we're going to be doing lower extremity. So next week is going to be like, legs and, your feet, ankles, things like that. And then for the third week, we're going to do spine, which is, of course, really, really important. Okay. But today we're starting with the upper extremity. So we're going to introduce what that kind of entails, talk about we're going to go over the bones and the muscles for the upper extremity again. And then we'll go from there. Other announcements that I have is that we have a new homework that's been posted. So I just posted that just this afternoon. So homework 2 is going to be due not this Wednesday, but the following Wednesday. So part of homework 2 is going to be going over kind of the muscles and joint stuff that we did last week. But also, some calculations on the upper extremity that we're going to be discussing this week as well. Okay, shouldn't take you too long. The conceptual questions, I think, we didn't get to go over everything in the conceptual questions in detail in the lecture. So you may have to look back through the lecture notes to find some of that information. But the calculations shouldn't take you too long. They're, we'll do them today. Hopefully you guys will be very familiar. So it's just very basic, free body diagrams, force balances, moment balances, things like that. Okay. All right, any questions I can answer before we get started for today? Okay, all right, so let's go ahead and get started. So the topic for this week is upper extremity biomechanics. Okay. All right. So, up until this point, we've kind of been just talking about, the different tissues of the body in general, right? So we've talked about bones, we talked about muscle, we talked about joints, right? That kind of, set the table for kind of what we're going to go over now, right? So now that we have a good understanding of, how bones behave, what their properties are, how muscles behave, their properties, we can kind of start to apply that, okay? So we're going to start with the upper extremity. So the upper extremity, I call it the upper extremity, but really it's just mostly just your shoulders and your arms. So that's your shoulder, your arms, your wrists, and your hands. And of course, the hands also include your fingers as well. Okay. And what's interesting about these parts of the body is that, if you compare them to the other parts of your body, the first thing you would notice that all the bones in the upper extremity, all the muscles, all the joints and all that stuff are all relatively smaller and more delicate. And there's a few reasons for this. So the primary reason is that, your upper extremity is not really, there's not really a biological need for them to have a lot of strength, because they're one of the only parts of your body that don't have to bear any weight. Because actually, most of the work that your body actually does is just kind of supporting its own weight, right? So if you think of your legs and your spine, your torso, all these kind of play a central role in bearing the weight of your body. But if you look at your arms are kind of off to the side, so they really only have to support their own weight, which is relatively small because they're not weight bearing structures themselves. Okay. And so because there's no real need for them to support any weight, that kind of reflects in kind of how large they are. Another reason they're a lot smaller is that they have a greater degree of motor control compared to other parts of your body as well. Right? And so if you remember from last Monday, we had the discussion of motor units and how muscles connect with the nervous system, right? So in your hands and your arms and your shoulders, you have quite a lot of nerves going to those because your upper extremity is responsible for a lot of the delicate movements that you do. Even something as simple as just writing notes on your paper, right? If you think about how much motor control that you have to do in order to do that, something that we don't really think about, it's really kind of astounding. Because if you try to use your feet to write your notes, most people wouldn't be successful at that because we generally don't have as much motor control over our feet as we do with our hands. Okay. And so I don't have the exact number, but the amount of nerves and the amount of motor units that are in your upper extremity, is greatly much bigger than the other parts of your body. And so that's all to say that the upper extremity is kind of responsible for what I like to the way that I like to describe it. Your upper extremity is your way to kind of interact with the world around you generally. Right? Right. It's interesting though, because generally when you see someone with like very large shoulders or very large arms, you think them to be a very muscular kind of person. But for those of you who work out, people always say you shouldn't skip leg day. And if you see someone that's kind of really incredibly top heavy, but doesn't have very strong legs, um, you know, then you kind of make a judgment of that person that they focus on the things that are visible, but really probably the more important muscles that you use for load bearing and taking the load off your skeleton, probably the someone with the bigger, better lower body is in better health overall than someone who's just super jacked arms and shoulders, right? Okay, so let's just quickly review the bones of the upper extremity. Okay. Okay. So there's eight bones to kind of note here. Okay, so I think so. The most central bone I would say is the humerus, which is your upper arm bone. So let's start with that. Okay. So that's your humerus, your upper arm bone. Okay. Then in your lower arm, you have two kind of bones that go parallel to each other. That's your radius and your ulna, right? So your radius kind of looks something like this. And your ulna kind of has a bigger head up here. Kind of comes down just like that. Okay. All right. So going down to your hand, you have also, of course, your carpal bones. Okay. So I'm not going to draw all of them. I'm just going to draw them kind of as one big kind of blob like this. Okay. But just know that, there's quite a lot of bones in here. Then, of course, you have your finger bones. Your finger bones are comprised of your metacarpals. So your metacarpals are the bones that connect directly to your carpals. And so those are the bones kind of at the base of your fingers. And then at the ends of the metacarpals, you have a couple more bones that are connected. So I'm not going to draw all of them, just because I'm out of space. But, these bones are known as your phalanges. Phalanges was like the favorite word of like my fourth grade teacher. Like, show your phalanges, everybody. And so we'd all kind of put our hands up. Okay. So coming back up to the top of the shoulder, there's one bone there's one bone that kind of comes in the back. This is known as your shoulder blade bone, right? So it's kind of in the background here, but it's kind of like triangular in shape. Okay. So this is your scapula, also known as the shoulder blade. Okay. And then the last bone that we'll talk about, it comes, right in front of the scapula here. So it's a little bit hard to draw from the 2D perspective. The scapula is kind of in the back, and then your other bone that I'm going to talk about kind of comes in the front. So it kind of looks like they're overlapping, right? So this other bone right here is known as your clavicle. And the clavicle, of course, is kind of informally known as the collarbone. Okay. So those are the main bones of the upper extremity. Okay, so a lot that we've seen before previously, but maybe a couple new ones as well. But as we kind of discuss this, as we kind of do example problems, I'm going to refer to these bones. So it's good to kind of have this figure here for you. Okay. Any questions on this so far? Okay. All right. So those are the bones. Let's go over the muscles of the upper extremity. Okay. So there are seven main muscles here. Okay. I'll do my best. I'm trying something new this year. I usually kind of present these as slides, but with how finicky this computer is, I thought I'd draw them, but I'm kind of regretting the choice right now. But we'll do our best. Okay. So there's seven muscles here. So again, let's kind of start near the top. Right. So we'll start with the shoulder muscle, right? All right. So right at the apex of the shoulder here, you kind of have a muscle that kind of wraps around the shoulder itself. That is your deltoid muscle. Okay. So let me kind of draw it just like this. And just to give you kind of a reference, back from our previous figure, the clavicle, your collarbone kind of runs kind of right in front of the deltoid. So the clavicle kind of runs this way like this. Okay? So the clavicle, of course, is not a muscle, but I'm just putting there as a point of reference. Okay. Okay. So right underneath the deltoid muscle is your chest muscle or the pectoralis, right? So the pectoralis muscle, the fibers kind of run this way, kind of like that. It's kind of like a trapezoidal looking muscle as well. Okay. All right. Then we get to your upper arm muscles. So there's three muscles in your upper arm that are all kind of responsible for kind of the same thing. So it's your biceps brachii, your brachialis, and your brachioradialis. Okay. It's kind of hard to tell them apart because they all kind of are in the same kind of area, but they all kind of run kind of parallel like this. Brachioradialis kind of comes through the middle, just like. So there's three kind of muscles here. So biceps brachii, brachioradialis, and brachialis. Most of the time, we don't really differentiate between those three just because they're all very so close to each other. But there are kind of three distinct muscles in there. Okay, even though they're all kind of responsible for the same motion, they're all kind of responsible for elbow flexion. Okay. Okay. All right. So that's kind of looking at the front of your bicep. And in fact, um let me just draw the muscles first, and then we'll talk about their actions. And then kind of in the back here, behind the arm, is your triceps muscle. Okay. So those are all the muscles of your upper extremity, or of your upper arm, excuse me. Okay. Let me draw this thing here. So this right here is your elbow joint. Okay. Okay. And then the other muscle that, for our analysis, we're going to be focusing, mostly on kind of the elbow, the action at the elbow. So we'll be talking a lot about kind of the biceps muscle, the triceps muscle, the deltoid muscles. There's of course muscles in your forearm as well, and that's when you need to kind of clench your wrist. But for our analysis, we're going to be focusing on these. There's one more muscle in the upper extremity that I do want to highlight. It kind of runs behind this person as well, but it's kind of like back here. Okay. More accurately, we kind of up here a little bit, but this is the latissimus dorsi. Okay. Your latissimus dorsi is kind of the shoulder muscle that goes kind of on top of your scapula. Okay. It's more kind of in your back. All right. Any questions on this? Okay. Yeah.
What your trapezius also included your upper extremity, or is that?
Your trapezius is kind of in the kind of upper back right here. So it's up there. It's just not what we're going to focus on in this section. Yeah. Okay. Okay. All right. So last thing I want to talk about are the joints. And I'll save you guys from looking at my drawings again. Yeah, when we do lower extremity, I'll show you guys the pictures. I'll bring a flash drive with the slides. Okay, so the joints in the upper extremity, we have five of them. You know, the top two are the ones we're really going to be focusing on, because those are the ones that are kind of more subject to injury. Okay. So the first one is the shoulder joint. Okay. Oftentimes, what you'll see in textbooks and things like that, the joints are often referred to by the bones that kind of connect the joint. Okay. So another name for the shoulder joint is the humeroscapular joint. So the shoulder joint is a ball and socket joint. That's formed by the head of the humerus and kind of the pit of the scapula. All right, so like we mentioned before, the shoulder joint is one of the most flexible joints in the body. It's probably the one with the greatest range of motion. Okay. But that also comes with a risk as well, because the shoulder joint is often dislocated, when people use it. Okay. Second joint is the elbow joint. Okay. And so your elbow joint is primarily a joint between your humerus, so the bottom end of the humerus and the ulna. Okay. So this is a hinge joint. So your elbow, primarily is just a flexion and extension type joint. You have the wrist joint. Okay. So your wrist joint primarily is also a hinge joint as well, although it can rotate a little bit, along its axis as well. Okay. So your wrist joint is primarily a joint between the radius, which is the other bone in your lower arm, and the carpus. And then finally, we have your finger joints. And so there's two types of finger joints. So there's the joint between your metacarpals and the carpals. So those are called your finger hand joints. And the other joint is between your phalanges and your metacarpal. So the joint between the ends of your fingers and the base. All right, any questions on that? Yeah, finger joints is mostly hinge joint. Yeah. The one that's different is your thumb. And so I think you'll hear people say your thumb is not technically a finger because it's you know, the bones are the same underneath, but the thumb is like a ball and socket joint. But for your other fingers, they're all hinge joints primarily. Yeah. Okay. All right, and so that was just kind of a quick refresher of all of those. And so, as we kind of go throughout the rest of the week, we'll be referring to them. Okay. But what we're going to be doing for the rest of the week is we're going to be doing what I call static biomechanical analysis. Okay. So static biomechanical analysis is going to take us up until the midterm, basically. Okay. And so the idea with static analysis to basically analyze the body when they're holding static positions. Okay. And so there's a couple kind of keywords there. So the first being static. And so static means no motion, right? So that means, we're going to look at cases where the velocity and acceleration of the body are zero. And so what that also means is that, when we do our kind of our force balances, all the forces and all the moments are going to be equal to zero. Okay. So essentially, what we're doing in this part is we're doing rigid body analysis, where we're going to be summing up the forces and summing up the moments on rigid bodies, and summing them up to zero. All right, so that's going to be kind of the central tenet of this kind of entire unit, right? So we're going to do sum of forces equal to zero. And so what forces are we looking for? So there are mainly three forces that we're looking for in each analysis. So the first thing that we're going to compute is we're going to be looking for the amount of the primary muscle force that's needed to kind of hold this position. So in every situation, there's going to be some, some force that the muscle needs to exert to hold the position. Okay. Most of the time, it's going to be to support some kind of weight or to support some kind of external force. Okay. So in every situation, or almost every situation that we're going to look at, there's going to be some kind of external force that's acting on the upper extremity. And then in order to oppose that, your muscles need to exert a certain force. Okay. And so we're interested in computing that. And the other thing that we're going to compute, usually we're going to compute two components of this, is the reaction forces at the joints. And so in our analysis, we're basically going to assume that our joints are kind of rigid, rigid supports or rigid constraints. And so in order to kind of balance everything out, there also needs to be some reaction forces there. And so we're going to be able to compute that from our analysis as well. Okay. And so usually there's two components of this that we need to compute. Okay. So that's three forces that we're typically, going to be solving for in each problem. And you might be wondering why the magic number is 3. And so because in this analysis, for this class, just for the sake of simplicity, we're going to be focusing mostly on 2D. Okay. And so in 2D analysis on a rigid body, we're kind of just limited to 3 governing equations, right? So we have the sum of the forces in the x direction is equal to 0. The sum of the forces in the y direction equal to 0. And we have the sum of the moments around a chosen point. Usually we sum the moments around the joint. That has to equal 0 as well. Okay. So we're going to have 3 equations. And so naturally with 3 equations, we're only going to be able to solve for 3 unknowns. Okay. If we were to do three-dimensional analysis, of course, is possible. It just becomes a lot more difficult to draw. You have 6 governing equations in that case. And so in 3D analysis, you have the sum of the forces in the x, y, and z directions. And you actually have 3 moment equations as well. So you have moments where the axis is the x direction, some of the moments when the axis is the y direction, and the sum of the moments when the axis is the z direction. Okay. But in 2D analysis, the only moment that we can kind of sum around is the moment about the z axis. Okay. And so that's the axis that's coming out of the page. Right. And so because for now we're kind of limited to just 3 governing equations, we can only really solve for 3 unknowns. Okay. Okay. Now, granted, there will be problems, and in real life, it's true too that there's more than one muscle force that's acting in a given situation. There's ways to compute that as well. We're just not up to it at this point. And so for those of you who are in one of my other classes this semester as well, the way that you actually do kind of proper biomechanical analysis actually requires the use of optimization, because it's a situation where you have more unknowns than there are equations, and so you would use optimization to kind of solve for that. But we're getting a little bit ahead of ourselves, and so we'll get there kind of later on. Okay. All right. Any questions on this before we jump into an example? Okay. All right. So let's do a simple example just to kind of get us started. Okay. Just so that we can get to know the process. So let's consider an elbow. Okay. Let's consider the elbow joint at 90 degrees flexion. So it's kind of making a right angle. In addition, we're going to assume that someone is holding some kind of box or some kind of weight in their hand. To keep things simple for this first example here, we're only going to consider the action of a single muscle. And so we're only going to consider the action of the biceps muscle. Okay. And so we're kind of lumping all three muscles of the biceps into one just for this. Okay. So let's draw a picture. So let's draw someone's arm like this. So let's say they're holding some kind of weight. Okay. That weight has a weight of W. Okay. And you can see from this image here that we are at 90 degrees flexion. Okay. So there's a perfect right angle at your elbow joint. All right. So what we want to compute first thing we want to compute here is the biceps force necessary for supporting this weight. And the other thing that we want to compute, if we assume that the elbow joint is a rigid hinge in this case, we're going to compute the reaction forces at the elbow joint as well. Okay. And so let's list our assumptions. So let's assume. First thing we're going to assume is that we only have one muscle here. Okay. We don't know the amount of that force, but we do know a few things about that force. Okay. Another thing that we're going to assume is that that muscle attaches a set distance of LM away from the elbow joint. Okay. So I'll show you kind of what that means in a second. Okay. Another thing that we're going to assume in this case is that the muscle force acts perpendicularly to the forearm. Okay. Most of the time, this is going to be true. So most of the time, not perpendicular, but most of the time you're going to know the direction of the muscle force. Okay. And that's pretty consistent with reality too, because a lot of times, if you want to find out what direction a muscle is going to exert force, you just need to run along the fibers. And so whichever direction the fibers are running, that's the direction the force is going to exert. Right? Because remember, muscles can only exert force in tension, right? And that tension force has to go along the fibers. All right, and the fourth thing that we're going to assume is that in addition to the weight that's at the end of the arm, well, we also know the length of the forearm as well. Actually, let me make that number 4. Okay. So we'll call that LW. Okay. Right, and so another way that you can interpret that is that the distance between the weight and the elbow joint is LW. Okay. And the fifth thing that we're going to assume is that in addition to the weight, the external weight that's being applied, we also have the weight of the forearm itself that's going to be playing a factor as well. Okay. So the weight of the forearm, we'll call that WA. Okay. Okay. So that weight of the forearm is known as well as the distance to the elbow joints. We'll call that L. Okay. Okay. So for this problem, because it's our first one, I'm being a little bit more deliberate, and so a lot of times I'm just going to draw you a figure, and a lot of this information is kind of implied from the figure. But just because it's our first time, I want to kind of list everything out, just so that it's okay. And so right after this, I'm going to draw a figure to kind of summarize all this, and in fact, we're going to use that figure as our free body diagram. All right, so before we do that, are there any questions on this? Okay, cool. All right, so your first step, after you kind of, read the problem, you kind of write everything down, is to draw your free body diagram, right? So your free body diagram is always going to be your first stop here. And you want to make sure that you do a nice job with this just so that you can see all the forces. Okay. Okay. So remember, this is a free body diagram of a rigid body. So, we're not going to draw just a point mass here, right? The actual dimensions of the body that we're considering is actually going to play a role because we need to sum moments as well. Okay. Now you don't have to draw kind of you don't have to draw kind of a photorealistic arm for a free body diagram. Usually I just use sticks, right? And so the rigid body that we're considering in this case is the forearm, and so I'm just using kind of a line here to kind of represent it. Okay. Of course, you can label this. Usually, it's kind of nice to do so. Right, and so the left-hand side will be the elbow, and then the right-hand side, this will be the hand. Okay. All right, so let's draw in all the information that we know, right? So the first thing that stands out to us is that we have the weight, the external weight that's acting at the hand, right? So we know that's going to be a downward force, okay, of an amount W, right? And so we're going to draw a downward vector that way. Okay. The other thing that we know from the assumptions is that we know the length of the forearm itself, right? And so, you can assume that, this person is holding the weight on his wrist, or, we're kind of centering on the wrist. Okay. So the total distance between your elbow joint and where the weight is acting, that's L. Okay. Okay, next let's draw the muscle force. And so, if we go back to our assumptions up here, we know a few things about the muscles, right? First of all, there's only one of them. So there's only one muscle that we are going to be considering in this case. Okay? And we know that it acts at a distance of LM away from the elbow joint. Okay? So if you notice, from these assumptions here, the elbow joint is kind of the center of kind of everything, right? So all the distances are measured relative to the elbow joint. All the angles are measured relative to the elbow joint. So, for most of these problems, there's going to be a central joint that kind of, is going to be the focal point of the analysis. And so it's good to kind of identify what that joint is. Okay, so let's draw that muscle force in. So we know that it acts at a distance of LM. Okay? So if we draw that distance from there, so that distance from the elbow to the force is LM. Typically, LM is going to be kind of a fairly short distance. One other thing that we know is that the force acts perpendicularly to the forearm itself, right? So that angle is 90 degrees. And if we assume that the forearm is also at 90 degrees, because of the 90-degree flexion of the elbow, then we know the muscle force is pointing straight up in this case. Okay. Okay. I want to talk about LM and the angle a bit more, but let's finish up this free body diagram. So we have a few more entries here. Okay. So the first one being the weight of the arm itself, right? So what do we know about the weight of the arm? So that's 0.5 there. So the weight of the forearm is WA, and it acts at a certain distance LA away from the elbow. Okay. Typically, we are going to consider the weight of the body segments in our analysis. Most of the time, we're going to assume that the weight kind of acts right in the middle of the body segment. Okay? But sometimes, because your body segments are not symmetrical, it may be off center a little bit, right? But it's going to be pretty close to the middle. And so we have another weight here. Okay? So we'll call this one WA. Okay. I moved it a little bit offset just so I'm not writing over that letter there. Okay. And we know that this distance here, this one is LA. So, excuse me. So the blue one here should be LW. Sorry about that. Okay. So the total distance of the forearm is LW, and then the distance from the elbow joint to the weight of the forearm is LA. Okay. So all of these forces are accounted for. There's two more forces that we need to put in the diagram, though, right? And so if we go back to kind of the original problem here, we know that we also need to compute the reaction forces at the elbow joint as well, right? Okay. Because what you're going to find out is that, in this particular problem, you're going to need some additional forces in order to kind of, stabilize this problem. Okay. And so at the elbow joint, we don't know what direction the elbow joint reaction forces are. And so we're going to include both of its components. Okay. So we're going to have a reaction force in the X direction. We'll call that JX. And then a reaction force in the Y direction, we'll call that JY. Okay. So these two right here, these are the joint reaction forces at the elbow. All right, so that's our free body diagram. So we have 5 forces that we need to account for. 2 of them are known, so the weight of the arm and the weight of the external force are known, but we have 3 unknown forces here, right? FM, JX, and JY. Any questions on this? Okay. All right, so to solve for these forces, we need to write out our equilibrium equations. Okay. So our three equilibrium equations are the sum of the forces in the x direction, sum of the forces in the y direction, and the sum of the moments, okay, in the z direction. Okay, so let's start with the sum of the forces first. Excuse me. That's probably the most straightforward way to start. Okay. So if we solve all the forces in the x direction, we only have one force in the x direction here, which is Jx. Okay. All the other forces are vertical, so we don't have to account for them in this equation. And in order for this to be at equilibrium, then the sum of all the forces in the x direction has to equal 0. Okay. All right, so from our first equation, we've already solved for one of the unknowns right away. In this situation, we don't have any reaction force in the x direction, okay? Which makes sense because all of our external forces here are all in the y direction, and even our muscle force, we've assumed it to be purely in just the vertical direction. Okay. Let's solve for the sum of the forces in the y direction. Okay. So another thing too, when you draw your joint reaction forces, I've kind of drawn them this way just because of habit. It doesn't really matter what direction you draw your reaction forces in, as long as you're consistent in your equations. Okay? So let me kind of write that here. Okay? There will come a time, when we're doing multi-segment analysis, where the direction will kind of matter a bit more. But we're only doing kind of single segment static analysis at this time, so the direction here doesn't matter all too much. Okay. But in this case, we drew JY going in the negative direction. So when we sum this up, we're gonna have a negative JY. Okay. Next force in the vertical direction is FM, so we're gonna have a positive FM. Okay. And then we have our two weights. And so we have the weight of the arm, WA, that's a minus WA. And then we have the weight of the external force, W, okay? Also in the negative direction, so we're gonna put a minus sign there. Right? And so all of that is gonna be equal to 0. Okay. So we can't solve this equation right now. We have two unknowns in that equation. We have JY and FM, so we kind of have to hang on to that for a second. But let's go ahead and finish up our moment equation here. Okay. So sum of the moments. So whenever you sum the moments on a rigid body, you can choose, where you want to sum the moments around, right? Probably, the way that it's been described to you in your previous statics course is that, you can choose the axis of rotation. Okay? Because when you compute a moment, a moment is different in nature to a force, because a moment is a rotational thing, right? And so a moment is a product of the force. Okay? In particular, it's actually the component of the force that faces perpendicular to the axis direction. Okay? It's a product of the force as well as the perpendicular distance between where that force vector acts and the axis of rotation. So in other words, it's a force and a distance. And so where you choose your axis, is actually a pretty important choice because, that's going to be, where you're going to sum up your forces from. Okay. And so a common choice, probably the choice you're going to make in every one of these problems is you're going to choose the axis of rotation to be the joint where the reaction forces are. Okay. There's a couple of reasons for this. And so the first reason is that, for most of these problems, most of the distances that are given to you or the dimensions that are given to you are going to be distances relative to the joint itself. So that kind of makes things easy for when you're computing or, multiplying distances by force to get moments, right? So everything's kind of already in the right form. But probably the most important reason is that, two of the unknowns that we're going to be looking for in almost every problem are the reaction forces at the joints. Okay. And so since we assume that the reaction forces act at the joint itself, okay, if we choose that as our axis of rotation, then the joint reaction forces are not going to show up in the moment equation because the distance between, the joint reaction force and the joint itself is 0. And so what that basically allows you to do is that it effectively eliminates two unknowns in your analysis, and you can solve the moment equation for just the muscle force. Okay. And in fact, this is a strategy that we're going to employ basically for almost every problem, where we're going to start with the moment equation, use that to solve for the muscle force first, and then we'll use that muscle force to then solve for the joint reaction forces from the force equations. Okay. Okay, so let's see what that kind of looks like in practice here, right? So I'm going to come back up to our free body diagram, right? And then I'm going to choose the elbow joint as the location where I'm going to sum the moments. Okay, so we're going to sum the moments around that point right there. Okay, so if we do that, we know that JX and JY are not going to contribute to the moment around that joint, right? And so we have three contributions to the moment equation. We have the contribution from the muscle force, and we have the two contributions from the two weights. Okay. Okay. So let's list out the moments from each of these, right? So remember, the moment is going to be the product of the force as well as the distance between that force and and wherever we're summing the moments around, right? So if we sum the moments, so if we take the component for FM, right, it's going to be FM multiplied by its distance to the elbow joint, which is LM. Okay. Next, we have the contribution from the weight of the forearm itself. Okay. And so we have WA, LA. Okay. I'll get to the signs in a second. Right? I know I haven't put any signs yet. I'm just writing out the three contributions just for now. Okay. And then we have the contribution from the external force itself, right? So that's W, and it's acting at a distance of LW. Okay. And we know that their sum is going to be equal to 0. All right. And so, of course, from this equation, I've omitted the signs because the signs that you choose for these moment contributions are going to be, really important. Okay. Okay. So, just and this is just kind of the way that I've been taught. But if the way that I do signs for moment equations, that if the moment would cause a clockwise rotation around the axis of rotation, then I usually give that a negative sign. Okay. Whereas if the moment that's caused by the force would cause a counterclockwise rotation around the joint, and I call that positive. Okay. So let's look at the three forces that we have here, and let's see what kind of rotation they would cause around the joint. Okay. Let's look at FM first. And so FM is pointing upwards, okay? And it's acting at a distance of LM to the right of the joint itself, right? And so if we follow this vector around, if we were to kind of curl it around our axis of rotation, right? So we know that it would go in this direction like this, right? We can see from that figure there that it would cause a counterclockwise rotation. So the moment that's contributed from the muscle force should be a positive contribution. Okay. Okay. Let's look at the same thing for WA and W, because those are going to be the same, right? So if you look at WA, right? So we kind of trace the arrow and then we kind of circle it around the joint like that. Okay. We can see that this rotation is going to be clockwise, right? Same thing for the external force W. And so we know that the contributions from these are going to be both negative. Okay. So we have a positive FMLM, negative WALA, negative WLW. Okay. Right. And now if we look at this equation right here, right? There's only one unknown in this equation. So that unknown is FM. Okay. Everything else is either known or we assume it to be known itself. All right, any questions on this? Okay. All right, so let's go ahead and solve this equation for FM. So let's solve the moment equation for FM. So it's just kind of simple arithmetic. So, what we're going to do is we're going to move everything that's not FM to the other side of the equation, divide both sides by LM. Okay. Then what we get in the end is FM is equal to WA, LA plus W, LW divided by LM. All right. So pretty straightforward result, right? It was a lot of talking, but we end up with something that's kind of straightforward here, right? So I really like to do these examples just in terms of the variables first, because there's a lot that you can kind of learn from an expression like this that'll tell you a lot about the system itself, right? I think kind of the tendency is, and I was like this too when I was a student. The tendency is always to kind of plug in numbers as soon as possible, to try to get the result as soon as possible. But for a class like this, where the equations are not overly complex, we're just basically just doing some force summations and moment summations. It's always good to kind of take a step back and look at your result in terms of the variables, to try to tell you, you can learn a little bit more about the system. Okay. So let's look at this result. And we'll talk about this result for probably the last 9 minutes of class today. Okay. So let's look at the terms in the numerator first. Okay. And remember what this equation is. So this equation is basically telling us how much muscle force that we need to support an external weight, right? Not only support the external weight, but also the weight of the arm itself. Okay. So first thing that we notice in the numerator is that the magnitude or the values of the weight themselves show up in the numerator of this expression. Okay. So why is that significant, right? And so if we were to increase the weight, right? So if we put more weight on this person's arms, so we increase the value of W, what's that going to do to FM? It's going to increase the muscle force that's required. And that makes sense, right? And so if you're carrying something heavier, intuitively we know this, right? So if you're carrying more weight, it's going to take more work or more exertion from your body in order to support that weight, right? That makes total sense. Okay. The other thing that shows up in the numerator is LA and LW, right? And so if you remember that was the length of the forearm itself. And LA was the location where the weight is applied, but the kind of the assumption is that the longer your arm is, the further away, your forearm weight is going to act as well. Okay. Anything that appears in the numerator of a result like this or the numerator of an equation means that your result is going to be directly proportional to that quantity. Okay. And so if the length of the arm appears in the numerator, what that tells us is that for people that have longer arms, then their muscles have to exert more weight in order to support whatever kind of external force. And that kind of lines up with our intuition as well, right? So people that are kind of longer, taller, we expect them to have more muscle mass compared to, people that are shorter, right? Not only is it, that they're carrying around more weight, but also it's just, they're just longer. So the amount of moment that's required to move or rotate a joint is going to be higher because of that. All right. But the last thing I want to talk about today, and probably the most interesting that we're going to talk about, is what's in the denominator of this expression. Okay, so the one quantity that's in the denominator of this expression is the Lm, right? So I didn't really define what Lm was, right? So let's kind of define that a bit more now. Okay. Lm is what we call the moment arm of the muscle. And the moment arm of the muscle is basically the perpendicular distance between where the muscle attaches to the joint that it acts upon. Okay. It's a very important quantity for almost every muscle in your body, right? And because it determines a lot in terms of how much force the muscle has to exert. Okay. Okay. So what you need to know about the moment arm is that typically for the vast majority of muscles in your body, the moment arm is usually very, very small. Right? And so generally your muscles are going to attach very close to the joint where it actuates on. Right? So just to give you some typical numbers, so if for the average person, the length of their forearm is about 32 to 35 centimeters. Okay. Okay. Right. So for a typical arm length, the muscle moment arm for these people is usually around 3 to 4 centimeters. So it's usually kind of 1 degree of magnitude less than the limb that it's acting on. Right? So what does that mean, right? And so if you actually plug in numbers for this equation, right? So let's plug in. Okay. So let's do a relatively modest weight. So we'll do a weight of about 80 newtons. Okay. The weight of the arm, we'll say it'd be about 20 newtons. Let's say that the muscle attachment arm is 4 centimeters. Okay. We'll say LA is about 15 centimeters, and then LW is 35 centimeters. Okay. Fairly typical values. Okay. All right, so if we plug all of these numbers in, we get a muscle force of about 775 newtons. Okay. Which, in the grand scheme of things, is not that much, right? But if you compare this muscle force compared to the external weight that you're supporting, right? So the weight that you're supporting in this problem is only about 80 newtons, right? And granted, we have the weight of the forearm itself that we're accounting for as well. But if you just compare these two magnitudes themselves, right, it's almost a 10x increase in the amount of weight or the amount of force that your muscle has to exert to kind of support a fairly modest weight, okay? And the main reason for that is this muscle moment arm right here, right? The fact that that's so small means that a lot of times your muscles are exerting, far more force than the actual external weight that's being performed. Okay. All right, so when we come back on Wednesday, we'll have kind of a deeper discussion of why that is, and so that's very typical for your body. It seems counterintuitive, but normally you would think that your body would want to exert less force, but there's a very, very good reason for that. Okay. All right, so thank you guys for coming today. Hope you guys enjoy the rest of your day, and I will see you guys on Wednesday.
I still gotta work on the deal with one more card and it's not.
Depending on how effective I am, you know, I find the daily. You're in for a layer for the ones that we want. Because, you know, well, like, but I didn't really for them, so. Run the notes, but, Oh. I got it, thank you.
Yep, see you guys.